This video clip is part of the EPFL introductory course on information computing and communication. Following an introductory clip on computer networking, this one is the first in a series of video clips on that subject. It discusses the fundamental notion of protocols and messages. The very first conceptual similarity between networking and storage is that both need to introduce structure in the information they manipulate. Imagine a signal arriving on a network without any structure. As seen in Module 2 of this ICC course, converting a digital bit stream into an analog electrical signal or vice versa requires coding conventions. But how a bit string is generated at one end of a network so it can be properly understood at the other end requires even many more conventions. Without more conventions, it would be impossible for a computer receiving that bit string to tell whether it is real information or just noise. Without more conventions, it would be impossible for that computer to know where real information starts and stops among the noise. Without more conventions, it would be impossible for that computer to know who sent the information. And without more conventions, it would be impossible for that computer to know how to interpret and understand that information. One might as well try to capture and understand an extraterrestrial message. All these necessary conventions are what makes up network protocols. A protocol is thus a set of rules that regulates communication. In fact, we use protocols every day in everything we say and write. For instance, how do we know where a communication starts and ends? Verbally, it is delimited by a short silence before and after we speak. In writing, a communication is contained in a postal envelope. But what is a silence or an envelope on a computer network? Who is communicating to whom? Verbally, speaker and listener are face-to-face. In writing, the communication is signed by the sender and addressed to the recipient. But how can sender and receiver be identified in a computer network? In what language is a communication taking place? Verbally and in writing, in some language that speaker, writer, and audience and reader recognize and understand. But how can computers agree on a common language? And what happens if a communication is perturbed by noise, for instance? Verbally, the listener says, "Sorry, I did not understand." In writing, a recipient can complain and ask for another copy. But what can a computer do in case of such errors? And in multi-party communication, how do the parties agree on whose turn it is to speak or to write? Verbally, everyone tries not to interrupt the speaker. In writing, parties can exchange messages simultaneously. But how can a blind and deaf computer know when it can send something without conflicting with others and swamping receivers? We try to answer these questions in the coming few slides to explain what makes up a protocol. Every communication between computers is made up of messages. Just as spoken language is delimited by short silences and written messages delimited by pieces of paper, possibly collected by paper clips, staples, or envelopes, electronic messages are delimited either by start and end markers on transmission lines or by an address pointer and a length field inside a computer. An oral or written communication may be composed of several subsequent messages. While a speaker speaks, her phone may ring, so she may interrupt her conversation by saying, "Excuse me a second," and resume after hanging up. Similarly, a journal or magazine subscription includes a number of subsequent editions of it. Some postal mailings may be so voluminous that they need to be sent in several separate envelopes. The same can happen in computer networking, where sending or streaming a huge file of information as one message would saturate a line or a part of the network. To deal with such occurrences, the information to be sent may need to be chopped up into several messages. In order to enable the receiving computer to put the pieces back together in the right order, each message typically needs to carry its own sequence number. To enable the sending computer to tell the network where a message should go, and to enable a receiving computer to know where that message came from, all messages typically carry a source and a destination address. Now, when people communicate verbally or in writing, they must use a commonly agreed upon language that all parties understand. The same goes for computers. Messages may be in different languages for communicating text, audio, video, images, etc., each with their own syntax and semantics. However, to enable the receiving computer to detect what language messages are written in, some, if not all messages, must carry a language type field explaining what sort of application they are a part of. In order to be able to cope with possible transmission errors and lost messages, messages often contain an error detection field called a cyclic redundancy check, CRC, which is a digest or a summary, a resume of the message itself. When a computer receives a message of which the CRC is equal to the digest that it can compute itself, this confirms that there has been no transmission error. In that case, the computer can send a positive acknowledgement telling the sender that the message, or several messages, were well received. Such an acknowledgement indicates that n more messages may be sent, where n is a so-called flow control window, preventing the sender from flooding the receiver with more information than it can swallow. To distinguish messages from acknowledgements, both are flagged with a bit or a field indicating whether they are a genuine message, indicated as MSG on this slide, or an acknowledgement. Of course, sometimes a received message may not be summarized by a digest matching the received cyclic redundancy check. Alternatively, a message may be completely lost, which the receiver would detect by one or more message sequence numbers or end of communication missing after some predefined timeout. In that case, the receiver should signal the sender by sending a negative acknowledgement, indicated by a 0 in the acknowledgement field, and bearing the sequence number of the first or the only missing message that needs to be resent. In summary, a protocol is made up of an exchange of sequences of messages and positive or negative acknowledgements. Both messages and acknowledgements contain a series of fields that allow communicating computers to follow the agreed-upon protocol. All of these fields together make up what is called the header of the message or of the acknowledgement. Acknowledgements often contain only a header and no message data, though in some protocols, acknowledgements do allow transferring message data as well.